Hey, we're all here. Awesome. All right, who do we got? 1, 2, 3. We're missing 3. Oh, 2. All right, I'll give it 1 more minute. Okay. Questions? Are there web work questions?
Oh, Professor,
Yeah. Hey, Amber.
I sent you an email that had my question.
Let me pull that up.
Yeah.
Sorry, I didn't get to that. Let's see.
No worries.
All right, let me find that. I was just looking at that last night. Let's see.
It was phase plane question.
Yep,
It was,
I got it. I got it. Let's see. Yeah, let's go over it. Yeah, so everything, I see everything you did was correct, but you're not getting the right answer for some reason. So let's go over it. Let's take a look at that. I'm going to share my iPad screen as usual. If it lets me. What do you all see? Do you see a blank screen? Oh. You seen a blank screen? Is it black?
Yeah, it's black.
yeah, it's black.
It's weird. Oh, there we go. Okay. All right. Okay, so let's see. You've got this system dx dt equals x times 3 minus x minus 4y. Y dt equals y times 1 minus 3x. And we're only looking at y, x comma y greater than 0. Okay, so let's see. Looks like you've done everything correct. Let's just try to sketch this, and then the last question there, which is what you had a question about, is about what happens to a particular point. So yeah, let's try to get a good sketch of what's going on here. So you're saying they say write an equation for the non-zero vertical x nullcline of this system. And that is, you say y equals minus a quarter x plus 3/4. So x nullcline is y equals minus 1/4 x plus 3/4. All right, so let's sketch that. And oh, let's add to that the y nullcline, you've got x equals 1/3.
Is it not showing up on the screen for anybody else? Are you writing on the screen right now?
I'm just writing on my iPad screen. You see it? Oh, you don't see it.
I don't see
It's just your
Oh,
blank.
How about now? Sorry about that. So there's the system at the top of the screen. Again, which one is this? This is number
It's number 3.
number 3. Okay. So for those of you who haven't done it yet, this is number 3. And the system they gave her, again, everybody's numbers may be a little different. The system they gave her is on the top of the screen there. It's this one. And then she computed the X null cline, the Y null cline, and it said she was getting the correct answer. So we're just going to go with this. And she also computed the equilibrium points. And she got, what did you get? 1/3 minus 1/12 plus 3/4, really? 1/3 minus a 12 plus 3/4. So that's minus, oh man. 3/4 is 9/12. So I think that's 8/12, which is 8/12 is 4/3. Is that right? 0, 0, and 3, 0.
I think it's 3/4 for 8/12 instead of 4/3.
3.
Or 2, sorry, 2/3.
2/3. That was right. Oh, because it's 0.67. Yeah. Better. Okay. Oh yeah, 8/12. So 2/3, of course. All right. So let's draw it. And then they're asking about the eventual fate of the point 1/3, 1, and what happens to that. And that's the question that Amber was confused about. So let's draw it. So, wow, that was terrible. So we've got the X null cline. So those are the places where, so the X null cline, Amber, those are the places you found where dx dt equals 0?
Yeah.
So when dx dt is 0, then all the vectors are going to be vertical. So we got to draw this thing. So this has a y-intercept of 3/4 and a negative slope of negative 1/4. Negative 1/4 is pretty shallow. Okay, and all along here, the vectors are all going to be vertical. And then we've got a y null cline of x equals 1/3. So x equals 1/3 is over here somewhere. And that's a vertical line. And all along there, the vectors are horizontal because their dy dt components are 0. And that tells us where those intersect. There has to be an equilibrium point because the only way to have something that's both vertical and horizontal is if it's just 0. And again, they're asking about the eventual fate of the point 1/3, 1. 1/3, 1 is up here somewhere. So what happens to that point? So good question. Let's see. So did you do any of the equilibrium point analysis?
What I did was I put 1/3 and I put the point 1/3 1 in dx dt.
Oh yeah. What'd you get?
And then I got something negative, right? Because if you just put in,
yeah. So if you get something negative, it's going to point to the left.
Yeah, but then according to the correct solution, it says that that point 1/3 1 goes to 3, 0, which is to the right of 1.
Yeah,
One
okay,
third.
so 3, 0 is over here.
Yeah.
And the other equilibrium points are 0, 0. So that's just those 3, 3, 0, 0, 0, yes. And 1/3, 2/3. Um, let's just check that real quick. So you're saying you plugged 1/3, comma 1 up here. And you got 1/3 times 3 minus 1/3 minus 4. And that certainly looks negative, doesn't it? 3 minus 1/3 is 2 and 2/3 minus 4 is going to be certainly less than 0. Yeah, that certainly looks negative. Let's check some of these other points. Well, what kind? Did you do the equilibrium point analysis on this point right here on that? Let's do
No.
this. Okay, let's do it. Let's see what we get. Actually, where are the other null clouds? Let's just fill in this picture. Let's really just kill this problem here. So when this equals 0, we're on that diagonal line, but we also have an x null cline where x equals 0. So if x equals 0, we're on the y-axis. So that gives us an x nullcline on the y-axis. So that's saying on the y-axis, everything's vertical. And same thing over here. When y equals 0, we're on the x-axis, and that's a y nullcline. So everything's horizontal on the x-axis. Okay. And I'm just going to make some guesses. I'm going to guess that if things are pointing to the left above this equilibrium point, then below they're pointing to the right. It's a guess. It's a pretty safe guess, but it's a guess. That means they're still pointing to the right here, which means they probably flip here and here. And let's see, we still have some ones we don't know. Let's check on the y-axis. Let's just check at some point on the y-axis. Let's just check some point at like up here at 0, 1. When x is 0 and y is 1. Let's plug those into the original equation. If x is 0, and that's all 0. Down here in the next equation, we get 1 times 1 minus 0, which is just 1, which is positive. So at that point, things point up, 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 up. That means they go up here, up. And then they probably flip. So it's looking like, if I had to guess, I would say the origin is a source. And this is probably what the picture looks like. So it looks like the origin's a source, which means things aren't going to converge to the origin. Right? So the question is, what happens to that point where the x is? And if I had to guess, I would say, yeah, what does happen? Yeah, what point do they want? 1/3, 1. Yeah, it looks like it does this, doesn't it? Certainly doesn't look like it converges to 3, 0. I think you're right. Tell you what, let's check it. So I'm going to share my screen. Um, oh, I share my screen. Oh, sorry. Share and oh, don't look at that yet. Okay, let's just type this in. What are you all seeing? Oh, you're seeing that window. I don't want you to see that window. Damn it. All right, hold on. You seeing my email now?
Yes.
Okay. Here's Amber's email. And we've got x times 3 minus x minus 4y. So I'm just going to type that into this graphing program. And let's check it out. X times 3 minus x minus 4y and y times 1 minus 3x. Cool. Zoom in a little more. All right, now we can really see what's going on. Everybody see there's a little 1 right here. If I can make this bigger. There's a 1 over here on the y-axis. We see that point, the equilibrium point here at 1/3. Tell you what, let's add to this some of those null clients just so we can see them. So she got y equals minus 1/4 x plus 3/4 minus 1/4 x plus 3/4. There's one of the null clients. And she also got x equals 1/3. Let's add that into the picture. There's the other one. Right, so there are those two null clients. And you can see they intersect right there where the vector field is doing some funny stuff, right? Because that's where the equilibrium point is. And it looks that from this picture now, it's pretty clear that that equilibrium point is a saddle, right? Because you've got things coming at it from two different directions and things leaving it from two different directions. And I think it's very clear that if I'm at this point up here, do you see where my cursor is? It looks like a little hand. I think it's pretty clear that if I'm at a point right there where that cursor is, and I just let it go, then it starts shooting up parallel to the y-axis. So it looks to me like it goes off to infinity. It goes off to where x is getting closer and closer to 0 and y is getting closer and closer to infinity. So I'm pretty confident based on this picture that their answer is certainly wrong. Yeah, good job, Amber. Everybody see that? If you have a point here, 1/3 comma 1, that's right about here, exactly right here, then that shoots up. There's a way to do this in this program. I don't remember what it is now. There's a way to actually click on a point and see where it goes. But there's no way a point that starts up here at 1/3 comma 1 is going to end up way over here at 3 comma 0. No, if we're up here at 1/3, 1, we're going to shoot up the y-axis. So it looks like somebody just manually typed in that answer and was incorrect. I think the answer they're giving you here was incorrect. I don't know what the drop-down options were. Do you remember, Amber, what it
Oh
was?
yeah, they were like diverge from, spiral to, spiral from.
I see. Yeah. Okay. Other Weber questions? Thanks for asking that, Amber. Nobody else? Okay, cool. Let's move on. New material. I hope the recorded lectures were somewhat understandable. I know I started rambling at some point, and I probably said some things that were wrong and then backed up and said some things that were corrected them. Let me go back to my iPad screen. I was working from memory, which is fine. There's nothing wrong with that. I'm certainly supposed to know this material. But I didn't have my book with me, so I couldn't compare the things I was doing to the stuff that's in the book. So I hope that I didn't say anything that was terribly incompatible with anything that was in the book and gave you the information you needed to do your homework. We're going to do some similar stuff now, the review, but the idea of what we're going to do now is to start delving into specific types of systems that occur really commonly within nature, and then use everything that we've learned to analyze those systems. And because of the structure of these particular systems, we're going to have some extra things, some extra tools too. So the first type of system that we're going to look at is we're in section 3.3. Which is called Hamiltonian Systems. So a Hamiltonian system is, there's something called a conserved quantity. So these systems typically happen in physical applications where you have some kind of energy that's conserved, like potential energy and kinetic energy is often the sum of the two energies in a mechanical system. And that sum, which is the total energy in the system, never changes. So things can get converted from potential energy to kinetic energy and back and forth. Another kind of system where you see these in is if you're doing economic modeling and you think about a town, for example, which is very isolated from the world, where there's a certain amount of cash within the town, right? There's a certain amount of money, and no money comes in or goes out, but the money flows from person to person or business to person, right? So the total amount of money in this town is constant, but you can still model the situation with a differential equation because there's this flow of money from one organization or one person to another, that sort of thing. Right? And you find these kinds of systems all over the place where there's some particular quantity that's staying constant overall, but that quantity gets distributed differently between potential and kinetic energy or between one business and another business. Okay? So these are all called Hamiltonian systems. And what we'll introduce here is some external function that represents that conserved quantity. So the example in the book is a good one that they start out with. So we might as well just jump right into that example. And then we'll look at a more physical example. And then some other questions like, what does it mean if your system's Hamiltonian? What effect does that have? So let's just jump right into the example in the book. The first example, the XDT is y, and dy dt equals x minus x squared. All right, so this is some system, and we can get some kind of feel for what system this is by just doing our typical analysis, and we'll do all that. We'll do the equilibrium point analysis. We could do null clines. We won't need to do null clines. But the thing you should know about this is that, as with any system, if you have a solution curve, if I give you an initial condition, then it's going to travel along some solution curve. And along that curve, along that trajectory, there is some quantity that represents the total energy of the system that's not going to change as you move along that curve. And at this point, there's no reason why you should recognize that. And the authors of the book just kind of jump right into it and say, hey, one of the authors, they treat this as a story, a lot of their things, and they point out that that this is a special kind of system that has a conserved quantity. Here's the quantity that's conserved. H of x comma y, I'll just write it out, is 1/2 y squared. It's not at all clear why you should see this. Eventually we'll see how you could come up with this on your own. But the point is that this quantity, if I just compute this quantity at every point of a solution curve, whoops, here's my solution curve. At every point of this solution curve, if I compute this quantity h, I get the same number. Right? So if I'm on some solution curve, every point on the curve has a value of x and y. I stick those values into this function, then I get the same number. Right? So it's like I'm traveling at some constant energy level. Or again, I'm in some economic system and the cash is flowing from one person or one organization to another in some way, but the total amount of cash is the same. So if I look at a solution curve, I can compute the amount of cash in that system at any given point on that curve, and it's constant. Now, what that means is that as I'm traveling along this curve, we're going to remember some Calc 3 here. As I travel along this curve, the value of h doesn't change. And another way to say that some quantity isn't changing is to say that its derivative with respect to time is 0. Right? So if I travel along solution curves, as long as I travel along a solution curve, h isn't changing. And another way to say h isn't changing is that its derivative with respect to time is 0. So let's just check this. We can actually check that the derivative of h with respect to time is 0 along solution curves without ever knowing what the solution curves are. I just sketched some random solution curves in that picture there on the right. But we don't have to know what the solution curves look like to be able to check that the derivative of h with respect to time is 0, because we have multivariable calculus. So let's just compute the derivative of h with respect to time, and remembering that h is a function of both x and y. And x and y themselves are functions of time. So we have h is a function of x and y, x is a function of time, and y is a function of time. So I need to compute the derivative of h with respect to time. And that's going to involve the multivariable chain rule, because we're composing multivariable functions here. H is a function of x and y, x is a function of time, y is a function of time. I'm composing those x and y functions with h, and then taking the derivative with respect to time. Maybe I should write that out a little better. I'm looking at the partial. Sorry, it's not a partial. It's not a partial. I just get a one variable function. Let me rewrite that. It's not a partial. I'm looking at h. That's a function of x and y. But x is a function of time and y is a function of time. So when I do those compositions, now I just have a function of time. And I'm going to take the derivative of h with respect to time. All right, multivariable chain rule. Does anybody remember it? All right. Does anybody remember the chain rule? What if h was just a function of one variable?
Isn't it like x of t, y prime of t plus y of t, x prime of t. Does it have something to do with
Close.
that?
Yeah, it's really close. Do this one. Just one variable. What's the one variable chain rule? What do I put here?
H prime x of t times x prime of t.
Yeah, now be careful because those primes, you're giving me derivatives, but it's the derivative with respect to what variable? They're different. So
Time.
yeah, well, for x, it's time, but not for h. What's the derivative of h with respect to?
With respect to x.
Good, yeah, right. So it's dh dx. Dx times dx dt. Right, this is a case where it's better to use that Leibniz notation where you, instead of using Newton's prime notation, you use Leibniz d whatever notation, because you really have to keep track of what you're differentiating with respect to. That's really the best way to write the chain rule. What about the multivariable chain rule? Anybody remember?
Does it look something like product rule?
It's a little bit like the product rule, yeah. It's basically the two derivatives you can do so that everything cancels. So if you think about the chain rule down here on the bottom of the screen, look, if these were actually just fractions, then the dx's would just cancel and you're left with dh dt. So there's two ways you can do that up top so that things cancel and you're left with dh dt. You could do the derivative of h with respect to x times dx dt. But you could also do the derivative of h with respect to y times dy dt. And the multivariable chain rule means you do both and you add them. So that gives you the derivative of h with respect to t as if you do both. But now we got to be a little bit careful because here, the derivative of h with respect to x, the notation's a little bit off because h is a function of both x and y. So now we're talking about a partial derivative. So instead of the d operator, I should be writing the partial operator. It's the partial of h with respect to x plus the partial of h with respect to y. It's still dx dt, not partial x with respect to time, because x is only a function of one variable. So we use a little d for functions with respect to one variable, and that script partial symbol for multivariable functions. Okay. Now, a lot of this stuff we can fill in. So going back, the partial of h with respect to x, we can fill that in because we know what h is. What's the partial of that function with respect to x? Just read it off. What do we get? Somebody tell me the partial of that function with respect to x is.
Minus x plus x squared.
Perfect. Good. Somebody else. What's the partial with respect to y?
Y.
Yeah, that's it. Just y. Good. All right. Now, where are we going to get dx dt from?
Isn't that just the differential equation?
Yeah, we're assuming we're sitting on a trajectory of this differential equation. So if we're sitting on a trajectory of that differential equation, we know what dx dt is. It's just y. Dx dt is y. And we know what dy dt is. It's x minus x squared. So we have minus x plus x squared times y plus x minus x squared times y. And the term in parentheses on the left is the negative of the term in parentheses on the right. So these just cancel and give us 0. Okay, so what was the point? The point was that we just confirmed this. Ooh, shoot, that shouldn't be there. We just confirmed this equation, that the derivative of h with respect to time is 0. And again, the reason why we're concerned about the derivative of h with respect to time being 0 is it says that h is a function which is constant on level curves, on trajectories, which is constant on solutions of the original differential equation. So h is what's called this conserved quantity. It's this constant energy function. So that if I'm traveling along a trajectory of the original differential equation, we know h has to be constant because its derivative with respect to time is 0. Got it? All right. Let's analyze this system a little better. Let's do it. Let's just do the whole thing. Right? Let's do the equilibrium point analysis. We've got dx dt equals y, dy dt equals x minus x squared. Dx dt equals y, dy dt equals x minus x squared. All right. Should just take us a few minutes. Equilibrium points. How do we get them?
Set both differential equations equal to 0.
Let them equal to 0. Okay. First one is easy. Y equals 0. Let's take that information and actually we can't even use that information in the second one. If x minus x squared equals 0, that's saying that x times 1 minus x equals 0. So x equals 0 or 1. So x equals 0 or 1 and y equals 0. So that gives us two equilibrium points, 0, 0 and 1, 0. All right, let's keep going. Let's look at the Jacobian matrix. So we take the partial of this first function with respect to x. What do we get? Partial of y with respect to x, 0. Partial of y with respect to y, 1. Partial of x minus x squared with respect to x.
1 minus 2x.
And partial with respect to y is 0. Now there's two equilibrium points we're worried about, 0, 0, and 1, 0. At 0, 0, we just get 0, 1, 1, 0. And at 1, 0, we get 0, 1. 1 minus 2 times 1 is negative 1, 0. Good so far? Okay. All right. Let's keep going. Let's look at what each of these are. So let's do them out of order. Let's do that. Let's do this one first. So we want the characteristic polynomial. So we've got minus lambda 1, minus 1, minus lambda. Take the determinant of that matrix and it gives us lambda squared minus negative 1 equals 0. So lambda squared equals minus 1. So lambda equals plus or minus I. So what is that? 1, 0? What kind of equilibrium point is that?
Center.
Center. Okay. And now let's look at 0, 0, where we have the matrix 0, 1, 1, 0. Subtract lambda. That gives us lambda squared minus 1 equals 0. So lambda squared equals 1. So lambda equals plus or minus 1. What is that?
Saddle.
Settle. Okay, let's go a little bit further on this one. So we've got the matrix 0, 1, 1, 0 times xy. Let's get the eigenvectors equals 1 times xy. So that tells us that y equals x, or x equals y, right? So we get an eigenvector of 1, 1 corresponding to the eigenvalue of lambda equals 1. So along 1, 1, we see a source. And then if we do the other one, lambda equals minus 1, then we get y equals minus x. So that's 1 minus 1 corresponding to lambda equals minus 1. So now we can draw it. We have two equilibrium points at 0, 0 and 1, 0. At 0, 0, we have the direction y equals x, where we have a source, the direction y equals minus x, where it looks like we have a sink, and then we have this center tangency around 1, 0, and it looks to me like things are going to have to be going this way to be consistent with the other arrows that I drew. So it looks like they have to go, what is that, clockwise. So I'm going to just kind of fill in what I think the rest of the picture probably looks like, something like this. Good? All right. Let me now switch over to my computer, and I want to show you some cool stuff. All right. You all see this program here? So you should be seeing my desktop now. So what you should be seeing is a vector field a lot like the one I just sketched out. So right here at 1, 0, we see this clockwise vector field moving around. And at 0, 0, it certainly looks like a saddle where things are moving away from the origin along the line y equals x, and along the line y equals minus x, things are moving toward the origin. Another interesting thing to plot here is the original function, the Hamiltonian function, that function h of x comma y, is that first one. And what you're seeing in this picture now, what I have it plotting, are the level curves of that. And one of the things to notice here is that the trajectories, the arrows, all the arrows of the vector field of the original differential equation look like they are parallel to the level curves of that function. For those of you who might be kind of rusty on what a level curve is, I can show it to you in 3 dimensions. Here is that function, 1/2 y squared minus 1/2 x squared plus 1/3 x cubed. That's what it looks like in 3 dimensions, that function h of x comma y. And we can plot the level curves in this case are just the contours. So here you can see those are the intersections of that surface with horizontal planes. And when I look at that face down, we see there's this kind of characteristic loop-de-loop, and everything else kind of goes all the way around it. I'm kind of zoom in a little bit. There, I've zoomed in a bit. You can see that bowl in the middle got bigger. One of the things we're not seeing, because I don't have enough level curves plotted, is we're not seeing any circles in the center here in this picture. So I could probably decrease the spacing of these contours till we start to see some of those. Oh yeah, there we go. You see those circles popping up in the middle there? So all those contours should remind you a lot of this 2-dimensional picture. They're the same contours, just a different view. Now the black lines in this picture, actually it looks like they're blue. The blue lines in this picture are again the contours of the same function, but we're just doing a 2D plot of it instead of a 3D plot in perspective. And the original differential equation we're seeing as arrows. And what it looks like is that the arrows are always pointing along level curves. And that's got to be true because the solution curves follow the arrows, and we've already proved that the solution curves stay at a constant value of h. And the constant values of h are exactly the level curves. Let's say I said h equal 5, right? That's a particular constant value of h. That picks out a horizontal plane at height 5 in 3 dimensions, and the intersection of that complicated surface with that horizontal plane at height 5 would be that particular contour, which would correspond to just one of those curves in this 3-dimensional picture. It would correspond to one of these curves in this 2-dimensional picture, which would mean it's one particular solution of the original differential equation. Is that making sense? There's this tie between this 3-dimensional picture and this 2-dimensional picture and the level curves of the function h and the solution curves of the original differential equation. And I think once you start seeing all the pieces of the puzzle fit together, then it starts to paint this kind of very beautiful picture here. One of the lessons here is that if you have a Hamiltonian system, so it's one of these systems where there's one of these conserved quantities, then there is this surface and all your trajectories are level curves of this surface. They're all contours. Another word for level curve is a contour of that surface. And that really kind of constrains the type of level curves you can see. If you think, let me go back to my iPad screen. Stop me if I'm saying gibberish, if you're confused about anything that I'm saying. Back on my iPad screen here. Oops. Hold on, I gotta rearrange my windows. Okay. If you imagine what level curves can look like for surfaces, well, if we have a surface that has a maxima, then the level curves can certainly look like circles. If we look at the top view of that, that's going to look like a point and then circles around it, which looks like a center tangency. Another thing you can see with surfaces is you can see a saddle. Right? We can see, it's hard to draw saddles, but let's see a saddle and there's this saddle point right here. So you see the level curves look like circles around this maxima, but then around this saddle point, from the top view, it looks like this equilibrium point just looks like a center tangency, but the other equilibrium point looks like there's this X going through it, and we see these other things. Right, so you've got equilibrium points corresponding to critical points of our original surface. And there's only 3 types of critical points of a surface. You've got maxima, minima, and saddles. So the level curves are just going to look like center tangencies for the maxima, minima, and saddles. That means there's all these other kinds of equilibrium points that we can't see. Right? We're not going to see spiral sinks or spiral sources or sinks or sources. Sinks and sources never look like, trajectories around sinks and sources never look like they're the level curves of some surface. So we can kind of confirm that that's true by doing some math here. So again, let's go back. So the one thing we know about this function, h, is that the derivative of h with respect to time is 0. Okay? And again, we can write that out by saying that means the partial of h with respect to x times dx dt plus the partial of h with respect to y times dy dt equals 0. All right, now that's going to happen when this is the negative of, let me get the signs right, because I could put the negative sign on one of 2 places, and I want to be consistent with the book. Yeah, this is equal to dy dt, and this is equal to the negative of dx dt. Everybody see that? If the partial of h with respect to x is dy dt, and the partial of h with respect to y is minus dx dt, then I know that this sum has to equal 0. Is that clear? I hope that's clear. All right, so going back to my original system, this is saying that dx dt in my original system is equal to the negative of the partial of my h function with respect to y, and dy dt is equal to the partial of my h function with respect to x. Okay, now originally, way back at the top, I said my x function was just, ooh, wrong one. There it is. My x function's just y, my y function's x minus x squared. So let's say we didn't know what h was. If there's a Hamiltonian function, if there's one of these h functions, then we know that its partial with respect to y is y. Its negative partial with respect to y is y. And its partial with respect to x is x minus x squared. So let's see, let's work backwards now. Let's see how they got that h function to begin with. Okay, if I know that I have a function and its derivative with respect to y is y, let's just forget about everything. So let's say I tell you right off the bat, I have a function, just some mystery function, and its derivative with respect to y is y. Then what was my function? Give me a function whose derivative with respect to y is y. Let's just go back to Calc 1. I have some function of y, and I tell you that f prime of y equals y. So what is this original function? I told you its derivative. You tell me the original thing. Somebody said it and I didn't hear you.
1/2 y squared.
Yeah, it's just the integral. Almost. It's 1/2 y squared plus some constant. Now that constant here is going to be really important. In fact, it's so important here that this is always the point when I tell my Calc 2 students that C right now is not important in Calc 2, but when you get to differential equations, it's going to be super important. This is actually the moment in time why it was drilled into your head never to forget about that C. Okay, because what's happening here is that we're looking at partials. it's no longer the derivative with respect to x, it's the partial with respect to x and the partial with respect to y, right? I have a function now, and I know from up here that, I'm going to take that negative sign and put it on the other side. I know I have some function h of x comma y, and all I'm telling you is that the partial of h with respect to y is negative y. And you may go ahead and say, oh, well, that means the original function is the integral, so it should be negative 1/2 y squared. And you would be almost right. That's the right answer plus some constant. But that constant might be a function of x. It's a constant as far as y is concerned, but not necessarily a constant as far as x is concerned. So we don't drill this into our calculus students' heads enough. So when you take the derivative of a function of x and y, and I take the derivative with respect to y, you all know the x's disappear if they're constants. When you do integrals, it's the exact opposite. If I have a multivariable function and I do its integral with respect to y, then the constants I get aren't necessarily numbers. They could be functions of x. Because as far as y is concerned, x is a constant. Does that make sense? Why I have a c of x here, not just a c? Just think about going forwards now. If I go forwards, when I take the partial with respect to y, that c of x term disappears. Okay? All right. Now, this is one clue. We're trying to figure out what this h function is. They told it to us at the very beginning, but let's see where they got it from, okay? So we have two clues. One clue is that the partial of h with respect to y is negative y. The other clue is that the partial of h with respect to x is x minus x squared. So let's just forget about this stuff for a minute. Again, we've got this mystery function h of x comma y. We're trying to figure out what that is. And now all we know is that the partial of h with respect to x is x minus x squared. So to go backwards, to figure out what h is, I've got to integrate that with respect to x. So what's the integral of x minus x squared with respect to x?
One half x squared minus 1/3 x cubed plus c.
Yeah, plus c, but c is a function of y now, right? Plus some constant function of y. So we have some constant function of y. All right, so now let's put it together. So I'm going to take this information and this information and try to put them together. I need one function, which is both 1/2 x squared minus 1/3 x cubed plus a constant function of y, but it's also minus 1/2 y squared plus a constant function of x. So how am I going to get that? It's somehow simultaneously both this one and this one.
It seems like the only two combining possibilities you could do are multiplication and addition. And if you do multiplication, it messes everything up.
Yeah, that's right. That's right. Well, I mean, we already know there's a plus and a plus, right? So the y part of it is 1/2 y squared, and the x part of it is 1/2 x squared plus minus 1/3 x cubed. So we get 1/2 x squared minus 1/3 x cubed, and we have minus 1/2 y squared. Right, this function is simultaneously of this form and of this form. Good. All right. So that's how they got it. This is the function that we were using, and what I was showing you on that graphing program is 1/2 x squared minus 1/3 y cubed minus 1/2 y squared. That's that h function they were getting. So they found that function because they knew the original system was Hamiltonian. Now that's a whole other thing, because how do you even know your system is Hamiltonian to begin with? So we'll look at that in a minute, right? So that's a different question. So we're assuming here our system is Hamiltonian. if it is Hamiltonian, then you'll be able to find this h function that is simultaneously satisfies oh, don't do that. If your system is Hamiltonian, then at the same time your dx dt function is computing the negative of partial h with respect to y, and your dy dt function is the partial of h with respect to x. So again, let me just say it again to emphasize. Whenever you're given a system of differential equations, you're given dx dt and dy dt. Now, if someone comes along and tells you this system is Hamiltonian, what they're saying is there's this h function, and that h function, you have two clues about it. That the dx dt function you're given is going to be the negative partial of this h function with respect to y. That's what this is saying. And the other clue you're given is that the partial of that net mystery h function with respect to x is what you're going to be given as dy dt. If you successfully find the h function based on those two clues, then you've confirmed that the system really is Hamiltonian. Let's go a little bit deeper. Let's think a little bit more. Right? If I have a Hamiltonian system, it means that the dx dt function is the negative of partial h with respect to y, and the dy dt function is partial h with respect to x. Now let's think about critical points of that system. To do the critical points, remember you have to do the Jacobian. The Jacobian is the matrix of partials. So the equilibrium point, not critical points, equilibrium points. The equilibrium points, how do I find the top left? Ooh, sorry, got a message about my son. Nice. How do I find the top left entry of those equilibrium points? What goes here?
Is it the second partial of h with respect to, well, first it would be with respect to y and then x.
Right, that's right. To find this first entry, I take the derivative of dx dt with respect to x, which means I'm taking the derivative of this thing with respect to x. And that's going to be the mixed partial, right? So it's going to be minus partial squared h partial x partial y. Okay. How about the next entry? What's that?
It's the negative partial squared of h, but both are with respect to x.
Almost.
Or respect to y, respect to x, sorry.
It's just with respect to y. Y and y. Right, I take the first function and I differentiate with respect to y to get the first entry. Sorry, x with respect to get the first entry. I take, no, I'm misspeaking. The derivative with respect to x gives you that, and the derivative with respect to y gives you that. And then same thing here, we're going to do the partial with respect to x and the partial with respect to y. So that gives us partial squared h partial x squared and partial squared h partial x partial y. All right, now, see you remember some multivariable calculus. What do you know about the mixed partials? Fundamental fact about mixed partials.
You can like flip them around, right?
Yeah, they're equal. partial respect to x, partial respect to y is always the same as partial respect to y, partial respect to x, right? So this is a really special matrix. If you have a Hamiltonian system, then the Jacobian matrix that you get of these partial derivatives always has diagonal elements that are equal and opposite. One's negative and one's positive, but they have the same absolute value because the mixed partials are always equal, right? So this is so I mean we can look at this a little more closely.
Professor, is that if and only if, or is it like, is the statement only like if you have a Hamiltonian, then you have that?
Yes. If you have a Hamiltonian, then you have a matrix of this form. Yeah. Yeah. If you have a Hamiltonian, then you find this function that satisfies both these simultaneously. And if you can do that, then your matrix has to be of this form. Yeah. And now let's look a little bit deeper. So let's just think in general. I have a matrix where I've got, let's see, what do we got? I've got negative some number. I've got negative some other number. I've got some third number. But then down here on the bottom right, I've got the negative of the top left entry. So I'm just kind of abstracting out. All I really know is that the diagonal elements are equal and opposite. And what I'm going to do here is I'm going to say, what are the possibilities? What can I possibly get for my equilibrium point? So if we just go ahead and do the equilibrium point analysis, we're going to subtract lambda, take the determinant, and we get minus a minus lambda times a minus lambda minus negative bc, which will be positive now, equals 0. Okay, that gives us minus a squared plus a lambda minus a lambda plus lambda squared plus bc. And now you're seeing something special happens, is that the lambda term disappears. That gives us lambda squared plus bc minus a squared equals 0. So lambda squared equals a squared minus bc. So lambda equals plus or minus the square root of a squared minus bc. All right, now two things can happen. Either a squared minus bc is greater than 0, or it's less than 0, or it equals 0, and we should think about that case a little separately. But the two most common cases is when that thing under the square root is greater than 0, and when that thing under the square root is less than 0. When it's greater than 0, then what kind of equilibrium point do I have?
Saddle?
Yeah, it's a saddle. Then I get a positive root and a negative root. And if it's less than 0, then I have plus or minus square root of negative number, which is a complex number with no real part.
Center.
So that's a center, good. So if I have a matrix of this form, then that proves that I either have a saddle or a center. We have to think a little bit about what happens if that's 0, in which case both eigenvalues are 0. If you have a system where both eigenvalues are 0, then it's just the 0 system. So we're never going to see that unless all of the entries of everything are just 0. Okay, so we don't have to worry about that case. So this kind of confirms this intuitive picture up top here that we already know that if there's this Hamiltonian function, h, then the trajectories are level curves of some surface. And you should remember from Calc 3 that level curves of a surface there's only two kinds of critical points you can have, three kinds. There's maxima, minima, and saddles. So the level curves either look like circles around maxima and minima, or they look like hyperbolas around the saddles. And that's exactly what we're finding down with the algebra at the bottom, which is that all we have are centers, which look like circular trajectories, or saddles, which give you these little hyperbolic trajectories. Right, so all these different perspectives are hopefully like coming together and falling into place. And now I see we have only 2 minutes left. One more very, very quick thing. This observation that the mixed partials are always equal to each other, that's a good way to check whether or not your original system was Hamiltonian. It doesn't always work, by the way, but it's a nice quick check. Is that we can differentiate the dx dt function with respect to x and the dy dt function with respect to y. And if they are equal and opposite, then there's some hope that this is Hamiltonian. Okay, so just as a quick example, I think the book has a quick example here.
What section is this in the book?
5.3.
Thank you.
Well, here, I don't know where it is, so I'm just going to make up a stupid one. Partial of x, sorry, no. I'm going to give you a system. Dx dt equals y, dy dt equals x plus y. There, I just made up a system. Okay, now if this were Hamiltonian, then this would be minus partial of h with respect to y, and this would be partial of h with respect to x. So if I differentiate this with the first one with respect to x and the second one with respect to y, I'm just picking up the mixed partials, which should be equal. Okay. Now, what is the partial of that first function with respect to x? Partial with respect to x gives us what?
0.
0. And what's the partial of the second function with respect to y? 1, good. And they are not equal and opposite. So there's no chance this is going to be Hamiltonian. Okay, it's just a quick test. If they are equal and opposite, it doesn't necessarily mean it's Hamiltonian, but actually most of the time it will be. I think most of the time it will be. So just a quick summary, because now we're really out of time. So I'll go in backwards order. So one way to check if you're dealing with a Hamiltonian system is to take the partial of the first function with respect to x and the second function with respect to y and see if they're equal and opposite. If they are, then it might be Hamiltonian. One way to find out, it's the only way to really check if it's Hamiltonian is to try to find that h function. And the way you do it is you take the first function and you integrate it with respect to y, and the second function you integrate it with respect to x, and then you see if you can reconcile the two answers you have with a single function. That gives you your h function. Once you have that h function, then you know solution curves of the original system are just level curves of that h function. So if you go back to Calc 3 and if you could imagine drawing that surface representing that h function and picture the contours, those are exactly the solution curves of the differential equations, the system of differential equations you're given. And you know for sure that the equilibrium points have to be centers and saddles. Okay, we covered a lot of ground there. So my recommendation is maybe rewatch the video of this lecture. Probably better if you just read the book. The book works through a bunch of other examples, some of which we've seen before. A good one that it works through is the pendulum. And actually, I may start class with this one next time because it's worth looking at that one. So the pendulum is another good example of a Hamiltonian system. It's a nice physical system where energy is conserved. And you can find that Hamiltonian function. Then we can plot that surface. Then we can look at the level curves. And then we can go ahead and go through and plot the trajectories of those by looking at the level curves. I think there are a few web work problems on this. I haven't gone through web work to find out. So I will check it and email you either some recommended problems from the book or tell you that you have web work problems. Any last questions? All good? Okay. All right. See you all on Wednesday.
Thank you.
Bye.
You.